So as we're wrapping up our second explore activity here, modeling and calculating redshift, a couple big ideas we want to pull in from this activity. So our big idea here, we had the rubber band. It's kind of our first demonstration. This one was the people walking, right? But also that like car sound. Those were kind of our two things that we connected here. So like we looked at this diagram here, our electromagnetic spectrum or diagram of all these different radiations. This is showing us that energy travels through space in waves. And the big energy that we're focused on here with redshift is visible light, right? So we know visible light travels through the universe in waves. And those waves can appear to change as the object is in motion. Now we thought about this first with the sound idea. So we heard that sound that we hear when cars drive by, right? That near sound where we're getting that change in sound wave because of the motion of the object. Higher pitch as it's coming at us, lower pitch as it moves away. While that's important, that's not our direct connection to the universe, right? We want to think about it in terms of what is this telling me about what's going on out there. So rather than continuing on with sound, we switched our thinking over to light, and we were looking at the differences in the red wavelengths compared to the blue wavelengths. And so we should have a couple characteristics that we can figure out really looking at this picture. I'm going to go a little bigger here. Oops. So our picture here, light waves in motion, this is a great visual review of what's going on with this red shift and motion of objects. So here we see our gentleman looking at a car from this direction. We see it has a different color and a different size relative to a car on this side of him. Again, different color, different size. And so this is a great visual representation of those big ideas we want to remember about visible light. Here, when we're looking at the red car, we notice a couple things. That car is moving away from the observer. It is, in fact, red in color, right? And it's a longer car, or therefore what we're thinking about, a longer wavelength. So when we see the light shift towards that red side out there in the universe, that gives me a clue that that object is moving away because of its longer wavelength. On the flip side, over here, the blue, again, the color is important. We call that the blue shift, and we notice that car is moving towards the observer, and it's meaning a shorter wavelength. And we noticed a couple relationships with those characteristics, right? Again, here's another visual. The object's going away from us. We notice that wavelength stretches out, therefore turns a little reddish. Opposite here. So with our data table that we looked at, thinking about relationships, well, if the wavelength is generally shorter, then we know that our redshift is less, right? We're not seeing as much of a movement away with that shorter wavelength. The longer that wavelength is, the bigger the redshift is, right? The further we know that object, and we can kind of circle that back to our rubber band activity, right? Galaxies, the farther away they are, the faster they're moving. So the more they red shift, the more they move away from us. Well, obviously they keep getting farther away, and that speed continues then to increase. We can see these numbers getting bigger as we go. So it's being able to recognize those characteristics of visible light, right? Again, that's our focus. These are all characteristics of visible light and how we can apply them to different things in space.